Take the numbers 2, 3, 5, 7, 11 and so on. They are known as prime numbers in a field of mathematics known as number theory. They only have divisors 1 and the number itself. Mathematicians from the ancient Greek had begun investigating the mysteries hidden behind this sequence of numbers, and one of the most fundamental properties of this sequence is that it grows to infinity. In other words, there are infinite number of prime numbers. In this video, I would like to present a classic proof of this fact by Euclid in one of his famous book Elements, and the another proof is by Christian Goldbach in a letter to Euler in 1730. Yes, he is the mathematician who had proposed one of the unsolved conjecture in modern number theory, the Goldbach conjecture. So the first proof by Euclid is actually pretty simple. We first assume, for the sake of contradiction, that there are finitely many prime numbers. Let's say P1, P2 up to Pk, which are all our primes. Then we will derive a contradiction by looking at the number n is equal to the product of P1, P2 up to Pk plus 1. The number n must have a divisor p. But because we have assumed that the number of prime numbers are finite, p must be one of the prime numbers P1, P2 up to Pk. This, however, means that p must divide n and the product of P1, P2 up to Pk. So p must also divide the difference of n and the product of P1, P2 up to Pk, which is 1. But prime numbers are bigger than 1, so p cannot divide 1, and this leads to a contradiction. And what have we contradicted? Well, it is our original assumption that the prime numbers are finite, so it must be the case that the number of primes is infinite, and that is what we want. The second proof is by Christian Goldbach, which uses a special type of numbers in number theory, which is called as the Fermat number, denoted by f of n is equal to 2 to the power of n plus 1, where n are the non-negative integers, which I think this special type of numbers deserve a video about it. Now we will show that any two Fermat numbers are relatively prime, meaning that they don't share any same prime divisor. In other words, the greatest common divisor of any two Fermat number is equal to 1. And this actually implies that there must be infinitely many prime numbers because each prime number can only divide one and only one Fermat number. And because Fermat numbers grow to infinity, if there are only finite number of primes, there must be a point where all the prime numbers are being used up. So the number of primes must be infinite. Returning to our proof, we show that any two Fermat number is relatively prime by using the following recursion, where if we take the product from k equals 0 to n minus 1 of f of k, it is equal to f of n minus 2 for n greater than or equal to 1. We will prove this recursion by using induction. The base case in this case clearly holds as f of 0 is 3, which is f of 1 minus 2. Then for the inductive hypothesis, we assume that this is true for the case n. Next, for the case n plus 1, we split the product from k equals 0 to n of f of k into the product of f of k from k equals 0 to n minus 1 times by f of n. Using our inductive hypothesis, this is the same as f of n minus 2 the whole thing times by f of n, which is the same thing as this following expression. This is a difference of 2 squares, which turns out to be just 2 to the power of n plus 1 minus 1, and that is just f of n plus 1 minus 2. This completes our inductive step. Now with this recursion, if we take two Fermat numbers f of k and f of n, where k is less than n, such that m is a common divisor of f of k and f of n, then m must divide 2. So m is equal to 1 or m is equal to 2. But m is equal to 2 clearly cannot be the case, since Fermat numbers are odd numbers. So m is equal to 1, and thus any two Fermat numbers are clearly relatively prime, which implies that there are infinitely many prime numbers. Now if you have reached here, make sure to subscribe to the channel for more math videos, and click the video on the screen right now to see more number theory proofs and I'll see you in that video.